All right, everybody. So today we're going to look at heat conduction, and we're actually going to try to look at heat conduction in 1D and in higher dimensions as well. So as usual, we start with the strong form of the problem, and of course you need some quantities, and I'm going to go through this very quick. So given your conductivity K from omega bar is a scalar, right? Remember that we define some things on the closure of the set, because we actually need to know the value also at the boundary. This is our thermal conductivity. F, which is our heat source, which is also a real. We're going to find U, or temperature field, such that and this is of course in omega, or we can say also for all x in omega. And if you remember Fourier's law, the heat flux can be written as k du dx, which basically says that heat flows in the negative direction of the gradient. This is Q, or is our heat flux, and of course this is what is called the Poisson equation. And of course we also need boundary conditions, and the same thing as we did for the elasticity in 1D applies here. You can have either a Dirichlet boundary condition, you can have a Newman boundary condition, or you can have a mixed or Robin boundary condition. So we can either prescribe the temperature. Remember, in my notation, everything that has an overbar is either the closure of a domain or a prescribed field, right? In this case is a prescribed temperature, and then we prescribe that on gamma U. And if you remember, gamma U is a symbol that we use to denote the part of the boundary with prescribed Dirichlet boundary condition. Then you can have a natural boundary condition, Ku dx, N is the normal. We did the same, and in this case we assume that heat flow, the convention that we use is that heat flow, if the heat flow Q at the ends of the bar is positive, then heat basically flows into the bar, and this is what we call Q bar, this the prescribed value of that quantity. And again, on gamma T, and I use gamma T not because it's attraction, but just to make the analogy with the same symbol that we used before in 1D. Remember, we also use gamma T to denote the part of the boundary with natural boundary condition. And then you can have a mixed type of boundary condition, K du dx, N is equal to H. And I'm going to change the notation that I use here compared to elasticity. I ran out of space, so I'm going to move this. On gamma H. And what you see here, this term here is our FEM coefficient, right? And basically this U infinity is our ambient temperature. All right? Okay. So now that we have our strong form, remember strong form is differential equation plus boundary conditions. We try to have this differential equation satisfied on average, and that is how we end up with the weak formulation. Okay. So as already done earlier today, thank you, Uri. We take our differential equation I'm gonna just copy this guy here. I'm gonna weight it with some weight function, and I'm going to integrate, and this is the way we are going to satisfy that equation on average for all w's in some space. And this is, of course, the beginning of our week. Yeah, so again, we do integration by parts. And so my term here well, I can actually just do it straight away here. And if you remember, this is a quantity that we just defined as Q. Okay? So then we take one. So of course, if you look at this term here, so we're basically replacing that term. So this one is negative, but it's going to the other side of the equation, as we saw earlier, and then it is going to become positive, and this is essentially going to be part of my bilinear form. And this term here, we call it, as usual, B of U W, and this whole thing to the right, L of W. And again, my abstract statement of the weak formulation is find the temperature field U that belongs to some space. Well, I was using E, let's keep using E, such that I also call it V in the lecture in the past. These are the same. As long as you understand what we're talking about, we're looking at functions in a space where strain energy, or what would be the equivalent in the heat conduction problem, is actually finite, right? So remember that in this particular case, E of omega is basically defined as the functions V such that V along the part of the boundary that has prescribed temperature, right, is equal to 0. Right, and if you remember, we also look at the case what happens when that is not the case, right? And we talked about what we call a linear variety to get around this issue that the two functions have to be still chosen from the same space. Okay, but this is a weak form, right? Now, in order to get to the Galerkin form, we just basically replace every U by UH and every W by WH, and then we get our discrete form of the problem. So I'm not going to repeat all that because it's obvious, but I'm going to just say here, we obtain our discrete equations by taking UH, WH belonging to some VH, I'm going to call it, that of course it's a subspace of my energy space. And then find UH, let's call it like this. And then let's just copy this very quick. And then everything becomes an H. And this here becomes a VH. Yeah, and if you remember the final discrete equations, well, if I take an equation or I take my approximate solution UH to basically be the sum of some shape functions multiplied by some coefficients UI, remember that it's a scalar field, so everything here is a scalar. And then we take our WH to be written the same way, right? And then when we plug this in, then we get our system KU equals F, where K is the global stiffness matrix that is obtained by assembling the contribution of all local stiffness matrix under case Ki. This is a local stiffness matrix, and the same with the force vector. The global force vector is obtained as the assembly of the contribution of all the finite elements. Okay, so very straightforward. Now we're going to jump immediately to the heat conduction in higher dimensions, and what you will see is that pretty much everything we did right now in 1D is the same in higher dimensions with one or two subtleties. So in higher dimensions, let's get started by just defining our mechanics potato. Okay, so there is, we call this omega, and of course there is still going to be a part of the boundary where we prescribe our Dirichlet boundary conditions. Let's call this part here where we prescribe our Robin boundary condition, let's call it gamma H, and everything else we're going to be calling it gamma T as before. Yeah, and well, just as a reminder, we're going to recall what we call as the gradient of a quantity, and the gradient and the divergence operators, right? Because when we move to higher dimensions, then we basically need to use the definitions of this. And if you remember, the gradient of a scalar is defined as the derivative of a scalar field, the derivative of s with respect to xi ei. So if you take a scalar field and you apply the gradient on it, you obtain a vector field. And if you take the gradient of a vector field, by definition is a tensor, and then basically is the derivative of vi with respect to xj ei tensor ej. Now if I take the divergence of a vector field, I basically reduce the rank of the tensor. In this case we obtain a scalar, and then is defined as the derivative of the if component of that vector with respect to xi. So you see, summation convention is implied. And then if you take the divergence of a tensor field, right, by definition is a vector, and by definition you take the aj component of that tensor, and then you apply the derivative with respect to xj ei. This is the way we define those operations. Okay, I forgot here when we define these parts of the boundary that normally, remember that we say that the boundary is basically, you can actually define it as the closure of the set minus the open set. That is the way normally people define. And you also say that this is basically the union of, I'm going to write it here, you can write it as the union of all those quantities. And again, I use the closure to denote the fact that, right, to make sure that I include the boundaries of those lower dimensional boundaries. Okay, and of course these are mutually exclusive. So remember, whenever you impose the temperature, you cannot impose the flux, and vice versa. And therefore, we express that condition as the intersection of all these sets, right, has to be equal to the empty set. That's normally the way people do it in papers. Okay. Okay, so now that we looked at these very simple definitions, we're ready to state the strong form of the boundary value problem, and it's exactly the same thing we did earlier. So we need some quantities. So given K, which in higher dimension is now a tensor, right? So the domain is, of course, omega bar is a tensor, and the way we express a tensor is in RD cross RD. This is the way we say that it is a tensor. We have F, which is our heat source, and this doesn't change. This is still a scalar field. We have our prescribed temperature, which doesn't change either. That is, sorry, gamma U here. And it's also a scalar field. Our heat flux from gamma Q to R. This is not the heat flux. Our heat flux is a vector, but remember that this Q bar, we have to dot it with the normal. Okay, that is where it becomes a scalar field. And H, which is our film coefficient, gamma H, is also a scalar field. Well, the strong form and following the same thing we did over and over is find my temperature field U such that, and for the heat conduction in higher dimensions, the equation is the divergence. This symbol here that you have here is the divergence operator, as I wrote it here. This is the way I define the divergence operator. Many people do it this way. You can also use div. So the divergence of K, which is a tensor applied to a vector, and if you remember, a tensor that is applying to a vector produces another vector. Okay? And therefore, this whole quantity here is a vector. When I apply the divergence, I get a scalar, right? And then that basically, I add a scalar field F, which is our heat source, is equal to 0, and this has to be valid in omega. And the boundary conditions, again, we have three kinds. We can have either U equals U bar on omega U. We can have a Newman boundary condition, grad U dotted with N is equal to Q bar on gamma T, and then K grad U dotted with N, and this is our Robin boundary condition, where H, in this case, we have assumed that it's a scalar. You could also have that as a tensor, but to make things simpler, let's just keep it as a scalar. So in other words, you can say that your film coefficient is going to change depending on the directions. In this case, we assume that it's basically constant throughout on gamma H. Okay, so what do we do now? We set up the weak formulation. So what do we do? Well, for the weak form, and you will see that it's all the same. So we take the equation, remember that this whole quantity is a scalar field. Yeah?
That's a good question.
Yeah, okay, go ahead.
The K and the U is a scalar field, right?
K is a tensor field.
K is a tensor field.
K is a tensor field.
And
K is our heat conductivity, that in this case is going to be a matrix, right? So you can have different conductivities in the X, Y, Z directions.
And U is also a tensor field?
U is a scalar field. This is the temperature.
Yeah.
Now, when you apply grad U, you get a vector.
Yeah. But, why is there, so I don't know what the notation is, but usually I'm used to 2 bars for tensor, but I only see
you mean the 2 dots?
no, 2 underlined.
Yeah, because K is the.
I don't use that notation. I don't use that notation at all. So for me, everything that has 1 bar under the symbol, it's either a vector or a tensor.
And capital letters or also.
You should know by, I mean, if you when you read a paper, and I don't adopt that notation because when you read a paper, you just see a bold symbol and that's it. So for me, this basically means bold. That's all it means. And of course, you have to understand what you're talking about, and therefore, the whether this is a vector or a tensor is from context, right? In papers, you're not going to find 2 bars underlining symbols. All right? Yeah.
The dot product then is obviously after the K bracket.
Yeah, of course. Because if you see here, we have. So again, grad U is a vector field. So if I applied a tensor to a vector, I get a vector. And now I dot it with another vector to get a scalar. Okay? All right. So again, I integrate over omega, and oh, I forgot to weight it with a weight function here. The omega, and I have this has to be satisfied on average in the domain. So that is going to be equal to 0 for all omega in some space. And now let's just change the notation altogether and let's start using V. It's the same as the E that I was using before, it's just a different symbol. Okay, so, and we do the same. So we look at this term, and you can see that from this term, the divergence of K applied to grad U, right, has in a way a second order derivative on the temperature field. So we would like to balance the derivative of that, and therefore we do integration by parts, right? We apply some identities here, which is essentially the same as doing integration by parts in higher dimensions. And when we do that, we balance derivatives, and balancing derivatives is good because we reduce the requirement that we impose on the functions that we're going to be using, and at the same time in the process, the natural boundary conditions arise. Yeah? And so, turns out that this term here it's part of this identity, and you can either trust me or just do it on your own. This is essentially the divergence of WK multiplied by grad U. And in essence, if you look just very quickly, you're basically applying the divergence here, right? So I have, again, grad U is a vector, tensor applied on a vector is a vector, right? So basically I have this W, which is a scalar field multiplied by a vector, right? So basically if I apply the divergence, I should get a scalar, right? And therefore, let's see on the other side. I have grad U is a vector, tensor applied on a vector, and then the other side is also a vector. The dot product between two vectors is a scalar. And then here, well, that is basically that term that we already discussed. Okay, you can also do component-wise and then check that this identity is true. But well, at the end, all we're interested right now is in replacing that, and that basically is going to take us to our balanced derivative term. And you can see already that the derivatives are balanced in that term. And then I'm going to put this term right here. Right, because what we're going to do is apply something called the divergence theorem on this term here. The divergence theorem just states, and you probably know this from previous courses, that if you apply the divergence of a quantity over the entire volume, right, that is essentially equal to that quantity dotted with the normal of that volume So you're basically transforming a volume integral into a boundary integral. That is essentially the divergence theorem. Yeah. So when we do that, this is going to be equal to the integral over the boundary of W k grad u, which is an internal quantity dotted with the normal vector, which I forgot here, but of course this boundary is going to have some normal vector field n. Okay, and of course I'm no longer in the omega, I'm on the gamma, so I'm now doing the integral on a lower dimensional manifold, no longer the volume, this is a surface. Okay, so when we do that, let's just write this again. Let me copy this. Actually, let me copy all of this. Yeah. Now, if you look at the last term, essentially, all we have there is more or less the boundary conditions that you have here. So what I'm going to do, because this last integral is essentially applied to the entire boundary, and we know that the boundary is composed by three parts. Remember, there is a part of the boundary where we're prescribing Dirichlet boundary condition. There is a part where we're prescribing Newman boundary condition, and there is one where we are prescribing Robin boundary condition. So we can actually just split that term into three components, right? So I'm going to, well, I'm going to keep it like this, and then I'm just going to copy all of this, because this is where we are going to replace those terms with the actual components. So you're going to have gamma t, and this is going to be, and then I'm going to put here WH U infinity minus U. And someone may say, well, what happened with the term where you are prescribing Dirichlet boundary condition? Who can ask that question? It disappeared, right? What happened to it?
Derivative of a constant.
Sorry?
You have the derivative of a constant.
No. Remember that when we are prescribing the Dirichlet boundary condition, we have a reactive term, right? And we are not interested in the reaction, right? So what did we do to get rid of that term in the past?
You have to separate the volume into functions, right?
No, that is to apply non-homogeneous essential boundary conditions.
Oh, well, when you have the Dirichlet, you have the vector of displacement, and you have to just cross the columns and rows.
Yeah, but we're not there yet. How? Because I could include here that term, right? I'm going to call it QR, like the reactive flux, you can call it, right? But I'm not interested in that. And remember that the way we go around it is by basically defining that these functions from this space W vanish at the part of the boundary with prescribed boundary condition. Like if you remember, we just did it in the one-dimensional case. We define our space that we're going to use, right, as some functions such that their value along Dirichlet boundaries is equal to 0. And we do this because we don't want to deal with reactive terms. That is why that term disappears. In other words, if I include one more term, which is the integral of gamma u of W times some, let's call it QR, that's the reactive flux, right? Then that W, this term, is actually going to be 0 there, so it just cancels out, and we don't deal with it. All right? Now, if you notice, this last term has two parts. It has one that is known. Remember, this is the environmental temperature, right? And then there is one that is unknown, which is U. So who can tell me what happens with each one of these two terms?
part will go to the bilinear.
Exactly. One part goes to the bilinear form, the other part stays in the linear form. Okay? So we can then rewrite this whole thing, and now we're going to replace that plus. Of course, the one that is negative is the one that goes to the other side. So we have gamma h of WHU d gamma is equal to this whole thing here. That I don't think I have enough space to put all that because I need to remove this. Let's see if that works. Still too. And that's it. And now you can clearly see that this term here is our bilinear form of U and W, and this whole thing is our linear form of W. So everything in the right hand side of this equation doesn't contain the unknown temperature field U. Everything that is on the left hand side doesn't. Okay, and therefore our weak form of the heat conduction boundary value problem in higher dimension again is find U belonging to some space of functions such that the bilinear form is equal to the linear form for all functions W in that same space. Yeah?
If you have a pure theory flat problem,
Yeah.
would that lead to rigid body modes in this case because it drops out of the equation?
No. No, we just remove those terms from the entire formulation because we don't want to calculate reactive fluxes right there, and because also we know the value, so there is really no point in doing extra computation.
Yeah, but if you would have a problem where you only have the flat boundary conditions,
Yeah.
I mean, they would affect the other points, right? So I don't really understand why they're not in the equations right here, if they do have an influence on the problem itself.
Okay. Remember that if you have a zero directly boundary condition, and that's all you have, then you are basically dealing with a trivial solution where the temperature field is zero everywhere. Now, you're talking about the case where you have non-zero temperature. And in that case, remember that whatever prescribed value of the temperature field you know is going to end up in the right-hand side, modifying your force vector.
Yeah.
That's what you mean. Yeah.
But I like the part where it drops out, I didn't really understand that part. Maybe it's just me.
It's just a choice. The choice is we just take functions from a space where those functions vanish in directly boundaries because we just don't want to deal with reactions. Yeah? It's just a choice. You can choose to keep them as well as part of the formulation. I've seen that actually in a couple of papers. People actually keep them. But it is really not necessary because if you really are interested in the reactions, then you can obtain it very easily by a post-processing step. Yeah, so, well, we are at the weak form, and we have still 15 minutes left. Well, and of course the rest is the same all over. In fact, from this point, since I'm in the abstract form of the weak formulation, to get to my discrete problem, my discrete finite element problem, is essentially taking a vector field UH and a test function field WH from the same space, our finite element space, and then we basically get to the same equations that I showed you earlier. It's just now that, well, there is absolutely no difference. The only difference now is that our finite elements are higher dimensional. Right? So in the 2D case, you are going to be dealing with triangles or quads. In 3D, brick elements, hexahedra, or tetrahedral elements. That's all there is to it. But for completion, let me just write it down so that whenever you see this, you see, well, it's not really over yet. So let's get to the finite element equations. But again, it's exactly the same thing as we did before. So we choose the trial solution and the weight function UH, WH belonging to this VH that again is a subset or subspace of V. And so VUH again can be written now as the product of vector of shape functions and some vector U that is local. So we're going to call it actually this in this context this is the entire U vector. It's just that of course when you look at the element, you pick the degrees of freedom that are relevant only for that that element, and that is because every element, remember that the nice thing about the finite element method is this idea that your shape functions are actually local, right? So that results in a stiffness matrix that is banded, right? And then WH is equal to the same. By the way, I'm just choosing the different notation here from what we saw in the one-dimensional case, but you understand that this is a dot product between the two vectors, which is the sum of UI multiplied times phi. So it's exactly the same thing. It's just that I try to do it sometimes in different ways because you are going to see this in different formats, right? When you read something, you may find it in one way or in another way, but this is exactly the same equation that I used in the one-dimensional case. Okay. All right. So when we do that, again, let me just copy this because it's exactly the same thing. So now we're dealing with finite dimensional functions and spaces, and that's it. And then this leads to our system of equations KU equals F that we solve for U. Yeah, so the moment I take UH in this form, remember that I'm replacing that UH in this equation. Right? So when I do this, this U is going to turn into a UH, this W is going to turn into a WH. So now I have to apply the derivatives of shape functions, right? And here the derivative of the shape functions, that is basically the outer product, and that is going to form a matrix in the implementation already of the local stiffness matrix. Well, there's no stiffness, but you see what I mean. It's like the equivalent in the heat conduction problem, right? And when I look at this term, here this W is going to turn into WH, and this U into UH, right? So remember, I'm now having this vector phi of shape functions. So here I'm going to have phi transpose phi. That is going to be the implementation of this term. And that is what you code in the computer to compute that integration. Right? And the same for the right-hand side, only that there is no U. So basically everything is going to be only one vector. So W is going to be basically a column vector of shape functions. The same here and the same here. Okay. So that's it for today. We covered heat conduction in 1D and in higher dimensions as well. As you can see, whatever we learn in the one-dimensional case is pretty much the same in higher dimensions. That's why I like to do this, because then if you really understand what's going on in 1D, to go to higher dimensions is essentially the same thing, right? The only thing that we looked in 3 dimensions, we use one identity that you can check if you want, and that we apply the divergence theorem to convert a volume integral into a surface integral. That's the only 2 differences. That divergence theorem in higher dimensions would be basically the equivalent to integration by parts in 1D. Any questions?
How can we define the shape functions in dimensions?
In higher dimensions. Okay, the shape functions in higher dimensions are a topic that I cannot cover right now, right? But essentially, we also use this idea of an isoparametric formulation. So the shape functions in a triangle, for example, are defined in a parent element, right? So if you, okay, let me just explain really quick here. So this is my master space. Let's call this psi eta, and this is basically my triangle. This is actually the type of element that we use in the finite element implementations. So let's say you have 3 nodes of the triangle. That is one node. That is one node. And that is the last node. And so your shape functions for this particular case is going to be 1 minus c minus eta, c and eta. These are your shape functions defined in parametric space for the triangle. And you can see, let's take the first one, right? When eta and c are equal to 0, I'm here at this node, the value is equal to 1, right? So if I move through in that line, when eta is equal to 0, the moment c is equal to 1, then that is equal to 0. And vice versa when I move into this other direction. That basically shows you a linear function that has a unit value at this node, right? And goes to 0 at this node and at this node. Okay? Now you can follow the same procedure with this guy here. The second shape function, when c is equal to 1, so this function is going to be equal to 1 here and 0 there. And the same with the last one. So these are defined in your master element coordinate space. The moment, of course, that we want to apply to a real triangle. So what's going to look like? Well, I'm going to have some triangle in real space that looks something like this. And using this idea of an isoparametric formulation, what we do is we basically describe the geometry, right, as the sum of shape functions phi that are a functions of c and eta multiplied by some functions of the coordinates of the element, right? And that is the way we do it. So of course in this context now I'm talking about these are coordinates, and this guy here is going to turn into a matrix, right? Because then you have to approximate the x component, and then you have to approximate the y component. But in any case, this whole thing is it's approximated in the same way as the field is approximated, and therefore you have an isoparametric formulation. But let me not keep this here because it's not part of this lecture, and if you see this, it may be confusing. Any other questions? Yeah?
The U and the W, are those still vectors? Or are they scalars?
No. This is scalars, huh? Did I make a mistake somewhere?
I think somewhere in between.
No, here I by the way, these are scalar fields, right? The temperature is still a scalar field regardless of the dimension. It's just that I chose to put U because now this vector is containing the degree of freedom of every node in your mesh. So therefore it's a vector, right? But the field is a scalar field. So this is the dot product between two vectors. Okay, right on time. I will post the video also later today so that you can watch it at your own pace at home. Thank you guys.